Hello everyone. In this video, I'm gonna give a quick introduction on mass spring oscillator because we're going to start working on linear second order equations and how to solve them. We've done the first order and we did the analytical methods and a numerical method. This is one of the application that is well known and most likely you've seen it somewhere, whether trigonometry or maybe even calculus or, or some other course or like physics. And but here we're going to work on it in details because differential equation is kind of the specialty here. All right. So when the spring is at rest, means equilibrium state, it's not compressed or it's not stretched, we get, for example, this state. And if it's a vertical situation, you can picture that. What's common between what we did before and now is the second law, which is Newton's second law. And that it governs here as well. And the acceleration is the second derivative of position with respect to time. Okay, so this you've seen. Now we just need to study what forces are applied for this system, right? Of course, let's scroll down. We have the force of the spring here with this stiffness K, which is opposite to Y because of course it's gonna be opposing the force that you apply to the spring. So when the mass M is displaced from equilibrium, the spring is stretched or compressed, and it exerts a force that resists the displacement, right? Because it resists displacement, it's going to be, it's going to have this negative, all right? And for most springs, this force is directly proportional, and we've done something directly proportional, means it increases with it and you multiply. Let's say here, we're using Y. And since it's opposing, it's going to be a negative. All right, so here where this positive, this constant here is positive and it's known as the stiffness. And of course, the negative sign explains what I mentioned. Okay, so you can go through it and you can look into Hooke's law, and which you've done in the past. And here you're going to get, once that happens, of course, you get these sinusoidal oscillations. And if there is no resistance, it's going to run kind nicely in the same way with these vibrations. If the spring is stiffer, then you see kind of the frequency increases. So the stiffness of the spring affects this frequency or the mass. So for here, for heavier mass, you see kind of the frequency is lower. So what else? What are other forces? So here it will keep continuing to build the model is to go through what forces can affect this system. So for the friction here, it's also opposing the force exerted on the spring. And so we will use this B, which is a damping coefficient, and with the first derivative of Y with respect to T, which is the velocity, all right? So that's another force that's going to be affecting it. It's friction. All right. So as you go through the details, you highlight, you write on the side, and you then what else can be there? So, of course, external forces. This is kind of important here because our main concern is external forces. Uh, so the other forces on the oscillator are usually regarded as external to the system, although they may be gravitational, electrical, magnetic, commonly as most important external forces uh, um, are transmitted by shaking the supports holding the system. So for the moment, we lump all the external forces into a single knowing this. So we're going to collect these forces into this F external with respect to time. And then the Newton's law, you see the second law again, um, becomes this mass spring oscillator, which is this. We're going to give it some change, some improvement. Okay. So that's kind of that, which gives us this in another way. Uh, the mass times the second derivative plus is damping coefficient times the first derivative plus the stiffness times the function or the position equal to the external forces. All right. So that's, and we will call it a little more in a way we are interested in it in a minute. So here you start asking, what do mass spring motions look like? Of course, is kind of what I talked about here when the oscillation happened, but let's read them. Um, so they resemble the sinusoidal functions, which are studied in trigonometry, with their amplitude dependent on, of course, initial displacement and the velocity. The frequency of oscillation increases with stiffer springs, but decreases with heavier masses, and that's what you see in the that I described in the figure I described there. Okay, so let's keep going. Okay, so now if you look at, let's verify if we take the equation and B is 0, and we have external forces are 0. Let's look at equation 3 and see whether the solution is in this form. And so if we take the equation 3, that means now we're looking at this to be 0. And it's equation 3. Okay. So and when you replace it, B is 0, external forces are 0, then it reduces to this. So now let's take this is just like plug and check, plug in and check. Just like when we started with the linear equations, we say, is this implicit solution, for example, or explicit solution or function, is it a solution to this differential equation? So same thing here. So the process is you're going to find y prime of t, then second derivative, then you will substitute here, but since this only uses the second and the first, then you will substitute just yt and or the function y of t and the second derivative y of t, and you will get this form, and which of course it is 0. Let's show it here. So if we do this, let's cosine omega t factor, then we get negative m plus omega squared plus k equals 0, which means negative m omega squared equal negative k, which means omega is k over m. And then we take a square root. So for here being positive, and of course, as you see, it does increase with stiffness, and it decreases with the mass, just like expected in the previous figure. Okay. All right, so let's keep going. We've done that process. It's similar here. Okay, so as you see, what if there is damping to it? You could run into, of course, in the previous B is 0 in this figure, and it keeps running and it's maintaining its amplitude. But here, if there is damping, different thing could happen. And like for A, it's kind of the oscillations are dying or decaying, or they are being damped slowly or low damping. And for the next one is like high damping, or it doesn't even the oscillation doesn't even happen. It's like it breaks it. So this is where we need to understand. It depends on the application. Sometimes you want it to keep running, let's say a music instrument or something, and sometimes you don't want it. You want the beat. You want or like a bridge, for example, or so, or the one I sent about the building. So you don't want, you want the vibration just to be damped completely or something like that. So let's see. I think yeah. So here they would explain 4.3, the damping is so dominant that it has prevented the system from oscillation. So you'll see here for 4.3a, the graph displays a damped oscillation, and damping has slowed the frequency, right? So and I think here so here they'll explain. So devices that are supposed to vibrate, like tuning forks or crystal oscillators, behave like 4.3a, the figure, and all right, and let's say for a car suspension, we want to have B. B is desired, right? To suppress these vibrations. Okay. So I think the idea starts to build, and we will get more to it and maybe do this, put some even codes or something to give different situations. All right, so I think this example just runs into the same thing of exploring the idea that if you have this solution uh, to equation three, and given the fact that you have or ignored external forces and the mass is 1 and the stiffness is 25 and the pin coefficient is 6, um, can we check this? So again, the process is the same. Y prime, Y double prime, substitute and collect and get 0. And because it's 0, then it is verified, yes. So I think you can do this. You can pause the video and try it. All right, let's see what's example 3. Example 3, same thing. External forces are still um, 0 and different values. However, I think here is the idea is for you to see um, when M, K, and B change, what type of solutions or what type of solutions or solution we're getting, right? So that's, I think, example 2 versus example 3. Look at, and this will help you a little more later when you solve to see. So you see here, when F is 0, F is 0, M is 1, M is 1, K is 25, K is 25. So these are, right, the same, but B is a 6 and B is a 10, an increase in B. We have the solution here has these parts, but for here we have this part, right? So I think so you can see what's going on. Yeah, the solution has changed because of how B changed. Okay, so let's see. I think if they talked about it here. So now if a mass of a spring system is driven by external force, so I think they just talk about the next if it's driven by external force. But let's see, I think if we have at the beginning here, if there is something between 2 and 3. All right, so example 2 has relatively low damping coefficient 6 and illustrates the solution of the underdamped case, which we'll see more in detail. Uh, um, and that's 43A. And example 3 is the damping is more severe, B is 10, and the solution is overdamped. Okay, so this is cool. So here, this is an example of underdamped. And for the next one, example 3, but this kind of runs through, so overdamped. Okay, so it's good to kind of try to see this and compare. We're not doing a lot of math here because we know how to do this math already, but the idea is to start understanding. So when we dive into the solutions and stuff, now we start connecting with these cases, and we can come back to these. All right, so now let's see the external forces. All right, so we have other figures here, which is for A and B. We have uh, in A a driving force and B a response. All right, so I think if you look here, uh, of course, we'll talk again about the applications. So you have common example of systems vibrating with this sync, um, which what happens is if there is a force that is applied to system, uh, the system is going to start to vibrate, and it probably reach that frequency, and it will be here in sync, and I'll explain that a little more later. But for now, just kind of examples which you're familiar with. Um, but let's talk about this one, uh, which is, of course, there is more. Here, the systems can be enormously sensitive to particular frequency omega at which they are driven. That accurately tuned musical notes can shatter fine crystal. Wind-induced vibrations at the right frequency can bring down a bridge. And there is a famous incident with Tacoma Bridge, which you can find online. Or of course here a dripping faucet can cause big headache, of course, yeah. So these resonance is where simple way now think about it, and then we'll talk more about it, is it causes the amplitude to go bigger. So this resonance response, for which the response have a maximum amplitude, may be quite destructive. Yeah, and you'll get examples on that. So let's, I think before you start thinking a little more about what's going on here, here is a nice example where find the synchronous response of the mass spring oscillator with these M equal 1, B equal 1, K equal 25 to the force. You see now the external force is not zero, but it causes the system, it's almost like it wants the system to go as, think about it as this sine function with omega t. So that's what we are going to be interested in, is how the system is going to behave because of these external forces. So here is a nice introduction to it through this example. So we know that equation 3, now based on what's given, is equals to that. All right, so we take the first derivative, we take the second derivative. We've done this, we know how to do, and you can pause the video and double check. Then now the right-hand side is this. But what will happen is, I think in many places, especially when you worked with partial fraction decomposition, you've done this match of coefficients. So we will say sine omega t. We'll see that we have a lot of terms here. But if we factor sine omega t, right, we have this factor here. Then we have a lot of terms with cosine omega t. So when you factor these for cosine omega t, you get this right-hand side, which means there is some cosine omega t here that can be written, but because it's not there, its coefficient is 0. So that's where the match is, to match now this left side with this right side, but really now it become this right side. So let's match these. So matching this is 1. That means this whole thing is 1. This left side and right side cannot equal to each other until the coefficients are the same, because these are the same. Right? So that must be 1, and this must be 0. Because for cosine omega t not to be on the left side, this factor here must be 0. And that's where this setup comes up, or this conclusion will come up, all right? So now what we will do, we're going to solve for A and B to get an idea on omega that causes resonance. All right. All right. So here, plotting kind of the profile of A. So here, as you see from the previous page, now we solved for A and we solved for B, and we get these. So now if you plot the profile of A and B, you get this figure here, 4.5. And you can see that for omega 5, this is with omega, at omega 5, you're going to have the highest amplitude, and that's resonance, right? So each time you can add these value with this value, this value with this value, just like if you're adding two functions, and and you can see for 5, you're getting these resonance there. Okay. All right. So to conclude this, um, this chapter is interested in differential equation. They are second order, and starting with linear, and particularly with coefficient A, B, and C, as we saw, to start being constant coefficients, right? And then we will be interested in this f of t. So let's see here. We will generalize our focus equations with non-constant afterwards, as well as to nonlinear equation. However, this equation is an excellent starting point because we are able to obtain explicit solution and observe and this and that. So what I mentioned, um, uh, f of t, you would see also something here. Um, uh, f of t or y of t, the solution is the unknown function that we seek, right? And this external force is going to be something that is known. So just like previously, we'll try to solve for, let's say, y of t, if, of course, if the dependent variable is y and the independent variable is t. And now before I close, of course, we're going to look at this overall as inertia times second derivative plus damping times first derivative plus stiffness times the function equal to external forces. So that's one nice way of trying to memorize it. Okay, thank you.